The universe is a vast and wondrous place, filled with swirling galaxies, brilliant stars, and planets of every imaginable kind. But scattered throughout this cosmic tapestry are objects of such profound strangeness that they challenge our very understanding of reality. These are the black holes. They are not empty spaces, but rather immense amounts of matter crushed into an infinitesimally small point. They are the universe's ultimate mystery boxes, silent and dark, holding secrets about the very nature of space, time, and gravity. What happens inside them is one of the greatest puzzles we have ever faced. It's a place where the rules that govern our everyday lives simply break down. For centuries, we have looked up at the night sky and tried to make sense of it all. We learned that stars are born from clouds of gas and dust, shine for billions of years, and eventually die. But some stars, the truly massive ones, end their lives in a way that is almost too fantastic to believe. They collapse under their own immense weight, creating a gravitational pull so powerful that nothing, not even light itself, can escape its grasp. Every black hole is surrounded by an invisible boundary, a line drawn in space-time from which there is no coming back. This is called the event horizon. Think of it like a waterfall on a perfectly calm river. You could be paddling in a canoe, floating gently along, and not even notice the current getting stronger. But there is a point, the very edge of the waterfall, where the water is moving too fast for you to paddle against it. No matter how hard you try, you are going over the edge. To escape the gravitational pull of a planet like Earth, a rocket needs to travel at a specific speed, known as the escape velocity. For Earth, that's about 11 kilometers per second. Now imagine an object so incredibly dense that its escape velocity is faster than the speed of light. Since nothing in the universe can travel faster than light, nothing can escape. The event horizon is that invisible circle in space. It is the point where the inward pull of gravity becomes infinite, and the cosmic drain of the black hole claims everything that crosses it. Throughout its life, a star is in a constant battle with itself. The nuclear fusion happening in its core creates a massive outward pressure, like a continuous explosion, which perfectly balances the inward crush of its own gravity. But eventually, the star runs out of nuclear fuel. With nothing to hold it up, the star's core collapses catastrophically under its own colossal weight. The material is squeezed into a space so unbelievably small that it becomes what physicists call a singularity. A singularity is a point of infinite density, where our current understanding of physics simply breaks down. According to Albert Einstein's theory of general relativity, gravity is not a force in the traditional sense, but a curvature of space-time caused by mass and energy. Think of space-time as a stretched rubber sheet. A black hole, however, doesn't just create a dimple. It punches a bottomless hole right through the sheet. Light, which always travels in a straight line, follows these curves in space-time. When it gets too close to a black hole, the curve is so extreme that the light's path bends back on itself, trapping it forever. Imagine you are an intrepid astronaut on a mission to explore a black hole from a safe distance, while your brave colleague decides to take the plunge. From your spaceship, you watch your friend fall towards the event horizon. As they get closer to the black hole, you would see their clock start to tick slower and slower compared to yours. This is a real effect predicted by Einstein, called gravitational time dilation. Their image would get dimmer and redder, as if they were fading away. They would seem to take an infinite amount of time to actually reach the horizon. But for your friend, the experience would be entirely different. As they looked back at your spaceship, they would see your clock, and indeed, the entire future of the universe, speeding up wildly. They would cross the event horizon without any particular drama. There is no wall, no sign, no bump in the road. For them, it is just another point in space, but one from which they can now never return. At the same time, the black hole's immense gravity would start to exert a powerful tidal force, a process delightfully named spaghettification. They would be stretched out like a long piece of spaghetti, torn apart atom by atom. In science, information has a very specific meaning. It's the unique identity of every single particle in the universe. Its location, its speed, its spin, its everything. A fundamental rule of physics is that information can never truly be destroyed. Think of it like burning a book. You might destroy the pages and turn the story into smoke and ash. But in principle, if you could collect every single atom, you could reconstruct the original book. Black holes seem to violate this sacred rule. When something falls into a black hole, all of its unique information appears to fall in with it, becoming lost to the outside universe forever. But then, in the 1970s, the brilliant Stephen Hawking made a startling discovery. He showed that due to quantum effects near the event horizon, black holes are not completely black. They slowly leak a faint glow of radiation, now known as Hawking radiation. This means that over immense timescales, a black hole will gradually lose mass, shrink, and eventually evaporate away. This is where the paradox truly bites. If the black hole evaporates completely, what happens to all the information it swallowed? This would mean that information is truly destroyed, which breaks the laws of quantum mechanics. The information paradox ignited one of the most famous scientific debates of the 20th century. On one side was Stephen Hawking, who initially argued that information was genuinely and irretrievably lost. On the other side were physicists like Gerard T. Hooft and Leonard Susskind. They were staunch defenders of quantum mechanics and insisted that information could not be destroyed no matter what. Susskind proposed that the information isn't lost at all, but is instead encoded on the surface of the event horizon itself, like a two-dimensional hologram that contains all the details of the three-dimensional objects that fell in. For decades, the debate raged on. Finally, in 2004, at a conference in Dublin, Stephen Hawking publicly conceded. He announced that he had been wrong and that information is indeed preserved. While the exact mechanism is still not agreed upon, the consensus among most physicists today is that the information somehow gets out, albeit in a highly scrambled form. You might be wondering why scientists get so worked up about something as abstract as information falling into a black hole. The reason this paradox matters so much is that it exposes a deep and fundamental crack in our understanding of the universe. For the last century, physics has been built on two great pillars: Einstein's general relativity, which flawlessly describes gravity, stars, and galaxies, and quantum mechanics, which perfectly describes atoms, particles, and their interactions. Both theories have been tested to incredible precision, except when they meet at a black hole. You cannot have both statements be true. They are in direct conflict. Solving the information paradox is about finding the next, deeper theory of reality that can unite gravity and quantum mechanics into a single, elegant framework, a theory of everything. This quest has profound implications for our understanding of the universe's origins. By understanding the singularity inside a black hole, we might gain crucial insights into the singularity that gave birth to our cosmos. The idea that our three-dimensional reality could be a projection of information stored on a distant two-dimensional surface is one of the most radical and exciting ideas in all of science. Black holes are not cosmic vacuum cleaners. If you were to replace our sun with a black hole of the exact same mass, the Earth and all the other planets would continue to orbit it just as they do now. Not all black holes are created equal. The smallest are stellar mass black holes, typically 5 to 20 times the mass of our sun. Then there are the supermassive black holes, the true giants of the cosmos. The one in our galactic backyard, named Sagittarius A, is more than 4 million times the mass of the sun. Black holes can spin, and they can spin incredibly fast. A spinning black hole drags space-time around with it, a bit like a rotating mixer paddle twisting honey. Inside the ergosphere, but outside the event horizon, it is impossible to stand still. Space-time itself is moving faster than light, so you would be forced to move along with the black hole's rotation. It's a cosmic no-loitering zone. So where do we stand today? The information paradox remains one of the most significant unsolved problems in theoretical physics. While most scientists now agree that information must escape an evaporating black hole, there is no consensus on exactly how it happens. The leading candidate leads to its own bizarre conclusion: a firewall. If the information is encoded in the radiation, then the event horizon must be a literal wall of fire that would incinerate anything attempting to cross it. Physicists are searching for a third option. Ideas range from quantum entanglement creating wormholes that transmit information out, to the possibility that space-time itself dissolves into a quantum foam near the horizon. The key to unlocking this mystery likely lies in a theory of quantum gravity. Theories like string theory and loop quantum gravity are our best attempts so far. proposing that space-time is made of tiny, discrete quantum bits. The answers are not yet written, and the final chapter of this cosmic story is still waiting for a new generation of scientists to discover it. The silent, dark mystery of the black hole continues to call to us, promising deeper truths about the cosmos we are privileged to inhabit. What excites physicists today is the knowledge that the solution will inevitably lead to a profound revolution in our understanding of what space, time, and information truly are.